Welcome back to our diesel training course. In the previous video, we have seen which polluting emissions are produced by diesel engines and made a brief mention of the solutions that the manufacturer has adopted to reduce them as much as possible. There is one element that stands out above all, which we will focus now: the exhaust gas recirculation valve. The exhaust gas recirculation valve allows the combustion gases to be reintroduced into circulation to make them react again during a subsequent engine cycle, reducing excess harmful substances and thus reducing the portion of pollutants present in the exhaust. This is where the EGR valve comes into play, which allows you to recover part of the exhaust gases containing water and carbon dioxide, significantly lowering the temperature in the combustion chamber and thus reducing the multiple valence nitrogen oxides, also called NOx, by up to 70%. Let's take a closer look at this process. In the diesel engine, the reintroduced gas is initially cooled in order to introduce a greater quantity of exhaust gas into the intake. This is possible thanks to a radiator placed in the part of the recirculation circuit leading to the intake manifold, which allows the exhaust gases to be reintroduced at a lower temperature, thus avoiding a peak in the combustion temperature. In order to adequately cool the exhaust gases, the valve uses hydraulic connections, which we can identify as tubes, connected directly to the cooling circuit, which in turn is connected to the radiator. This type of exhaust gas recirculation valve is often installed in vehicles equipped with a particulate filter, for which, during the regeneration phase, the gas temperature is kept high to help the cleaning process, which takes place thermally. However, there are also recirculation valves that do not provide for a preventative cooling of the exhaust gases, and these use the acronym HGR, hot gas recirculation. The cooling of the reintroduced gases causes condensation, which in the long run generates deposits of carbonaceous material, which tend to solidify and create malfunctions of the valve itself. Many of the exhaust gas recirculation valves built today also have an electric or pneumatic bypass valve, which avoids the cooling that can occur. For example, during the heating phase to quickly bring the engine and the catalyst to their optimum operating temperature. This is useful for reducing the noise typical of diesel engines and the raw emissions of hydrocarbons, and during the regeneration phase of the diesel particulate filter. The exhaust gas recirculation valve, controlled directly by the engine control unit, adjusts the amount of exhaust gases being reintroduced into the intake based on the engine operating status determined by some maps stored in the original calibration file of the control unit itself. When the exhaust gas recirculation valve is commanded to open, less oxygen flows inside each cylinder, and this lowers the performance that the engine generates. When the exhaust gas recirculation valve is commanded to close, for example during overtaking when the accelerator pedal is fully depressed, the oxygen inside the cylinder will be the maximum value and the performance delivered by the engine will be high. Precisely for this reason, tuners often want to be able to deactivate the exhaust gas recirculation, since the reduction of oxygen also determines a not insignificant reduction in engine torque, as the space inside the cylinders available for air is occupied by exhaust gas. There are various types of exhaust gas recirculation valves, but the main ones are divided into two categories: pneumatic, electric. The vast majority of early production valves up to Euro 3 emission standards featured an inward opening poppet valve, which was operated by a vacuum actuator. The first versions of the pneumatic exhaust gas recirculation valve did not have any electrical signal controlling it, but rather a shaft connected to a diaphragm in the vacuum cylinder. Compared to an electrically operated exhaust gas recirculation valve, the main advantage of the pneumatic valve is low cost, robustness, high temperature resistance, and compactness. Electric exhaust gas recirculation valves have now become the standard thanks to faster and more precise control, which adapts to more stringent emission standards. The modern electric EGR valves, regardless of whether they are installed in a low or high pressure exhaust gas recirculation system, consist of the following elements: The valve, which opens and closes, varies the passage area of the exhaust gases. The actuator, an electrical component that provides the force necessary to physically open or close the valve. The valve body, which contains the valve, actuator, return spring, and other mechanical components. The position sensor, which transmits the valve position to the engine central unit. The external part of the valve, which contains the position sensor and the electrical connections. The actuator of the exhaust gas recirculation valve just described can be controlled by 3 different types of actuation. A solenoid. An electromagnet generates an oriented magnetic field. When the electric current passes through the coil, the generated magnetic field pulls a metal spindle which opens the valve. In the absence of current, the EGR valve remains closed. The main advantages of this technology are that it has a very low solenoid response time, 50 to 100 milliseconds, uses direct actuation of the valve, while the disadvantages are a weak implementation force, one-way actuation, opening, and high electrical consumption. Direct current motor. This is currently the type most commonly used in modern engines to control the EGR valve. The duty cycle motor contains a rotor, consisting of a metal core with copper winding, and a stator, consisting of permanent magnets whose magnetic flux crosses the rotor, while the narrow space between the two components is called an air gap. The torque produced by DC motors is converted into a linear drive force via a system of mechanical gears and levers. The position of the exhaust gas recirculation valve, driven by a duty cycle motor, can only be determined using a position sensor. This provides the engine control unit with a signal proportional to its supply voltage of 5 volts, thus allowing diagnosis of the valve itself and calculation of the flow of the exhaust gas as reintroduced by it. The main advantages of this technology are that it has a very high valve actuation force and a low response time, less than 100 milliseconds, while the disadvantages are its sensitivity to vibrations and high temperatures. The mechanical system is subject to failure, has high electrical consumption, and is highly affected by external electromagnetic disturbances. Stepper motor. The rotor contains a series of permanent magnets and the stator contains a series of electromagnets, consisting of coils with an iron core, controlled by an electronic power circuit. The rotation is produced from the interaction of the rotor and the magnetic field generated in the electromagnets. The stepper motor is capable of reversing rotation without the need for a gear mechanism. The main advantages of this technology are that it is a very simple system. It is compact, while the disadvantages are that it is not very accurate, has a slow response time, 200 milliseconds. To increase the efficiency of the operation of the exhaust gas recirculation valve, throttle bodies are also present on diesel engines. Based on the percentage of opening of the swirl valves, also controlled by the engine electronics, it is possible to generate a differential pressure in the flow of air flowing towards the cylinders that allows the recirculating gases to be sucked in. Through the mass airflow sensor, placed in the intake duct after the air filter and before the throttle body, it is possible to regulate the rate of reintroduced gas with sufficient precision and, thanks to the sensor, the mass of the reintroduced gas is calculated indirectly. As the difference between the total air mass entering the engine with EGR valve closed and the instant air mass entering the engine with EGR valve open. So, the difference between the airflow that would occur with the EGR valve closed compared to that which actually occurs with the valve open defines the flow of recirculating gas. Let's clarify the concept and take a look at a typical exhaust gas recirculation control map present in an original file of a diesel engine. The map in question shows us, according to the engine speed, the quantity of exhaust gas to be reintroduced into the intake, indicated in milligrams of exhaust gas to be reintroduced for each cycle. Thanks to these maps, it is, therefore, possible to portion the exhaust gases managed by the EGR valve or decide to limit their reintroduction as much as possible. This type of management is not the only method that the car manufacturer may adopt. On some older generation control units, in fact, it is possible to find maps that physically manage the opening or closing of the valve. In fact, in this map we find values expressed as a percentage of opening of the exhaust gas recirculation valve, and reference axes reflecting the engine revolutions and the volume of fuel to be injected. We can immediately note that the manufacturer already provides for the closure of the EGR valve in the event of high engine speed or high volume of fuel to be injected, which can be translated as high performance required. While when the engine RPMs are at a minimum, the opening percentage of the exhaust gas recirculation valve is high, specifically to reduce polluting emissions as much as possible. Also in this case, it is possible to modify the map shown to increase the intake of air from the outside and, consequently, the performance delivered by the engine. Finally, let's quickly examine the intake system of a diesel engine, in particular, the function of the high-pressure EGR valve and of the low-pressure EGR valve. As we can see from this diagram, the high-pressure exhaust gas recirculation valve is positioned immediately downstream of the exhaust manifolds and allows the intake gases to be reintroduced after appropriate cooling without passing through the turbocharger. However, this system has obvious drawbacks. It significantly increases the temperatures in the intake system. It limits the boost pressure and it reduces engine efficiency in terms of fuel consumption and performance. Furthermore, this system makes it possible to comply with emissions classes up to Euro 6A, first version. Precisely for this reason, an additional valve was necessary, thus overcoming the most stringent emissions regulations, the low-pressure EGR valve. A low-pressure exhaust gas recirculation system is necessary in order to bring the quantity to be reintroduced downstream of the particulate filter where the pressure is lower. The gases are cooled thanks to a heat exchanger and subsequently brought to the turbine, thus increasing the turbo pressure. The air entering the intake manifolds is further cooled before entering the combustion chamber by the intercooler. This system, compared to the one defined above, stands out for numerous advantages. It allows an increase in the gas recirculation rate, keeping the intake temperature under control, reduces the oxygen in the incoming air to, in turn, reduce nitrogen monoxides, NOx, provides greater engine performance due to better turbo response, produces greater pressure inside the cylinder, especially at partial loads. In summary, in this chapter, we looked at the operation of the EGR valve, the types of valves that can be installed in diesel engines, then focused more specifically on how this component is managed by the engine control unit, and finally, the composition of the system, which includes both high-pressure and low-pressure exhaust gas recirculation. That's all for now. See you at the next step.